Hello students, in previous session we have seen the introductory part of the transmission shaft, that is unit number 2, which is mentioned in a syllabus, design of shaft, keys and coupling. So in that we have seen what is transmission shaft, how it structure is designed and how it can be utilized, what are the materials are required, what are the types of the transmission shaft, that we have seen in previous session. Now today I am going to tell you the design derivation on the shaft design. Basically, there are two kinds of the shaft. One is solid shaft, second one is hollow shaft. So we'll start with the solid shaft. Again, solid shaft can be designed on a 2-point. As like first type is solid shaft designed on the basis of strength. Second, solid shaft is designed on the basis of rigidity, that is twisting. So that we need to find out. So one by one we'll see. So first of all, I'll start with the shaft design on the basis of strength for solid shaft. Of course, for solid shaft. Now, for solid shaft, we'll have to design. We have to consider the things. Solid means like this shaft is there. It is having structure like this, which is having bearings, two ends, and this will be the shaft. Now, while designing this, we are going to consider the shaft design always small d diameter. Now while designing this, first of all we have to consider the conditions, what kind of the stresses are coming on the shaft, because this shaft is performing the transmission of the motion as well as a torque as well as a power, while pulley is mounted on the shaft, while gear is mounted on the shaft, while sprocket is mounted on the shaft. So that we are going to consider here. So load condition we need to consider. So for that, while designing the shaft, we'll have to be very clear that what kind of the loads are coming on the shaft. So basically there are the three kinds of the load coming on the shaft. First one you can see, first one is tensile load. Why? Because see, load is acting and the bearings are connected at the two ends. So first load is, we'll have to consider a tensile. So while tensile is there, tensile load is there, we'll have to calculate tensile stress always. Where there is a bending stress. So likewise. So I'll write first is tensile stress. Notation sigma T. This will be the tensile. Now calculating this, we know stress is nothing but load by area. So that we'll have to find sigma T is equal to, load means P divided by area. So here load is, we can calculate or we will get directly, and area, the shaft is having circular cross section. You can see here what happened, the cross section is always circular. So while circular cross section, it means its area is pi by 4 d square. So this will be the area. Now again I simplify this, 4p by pi d square, equation 1. So this is about the shaft design on the basis of tensile strength, while designing strength, tensile. Now we'll see the bending, because there might be chances of the bending. So here I'll write second is bending stress. Bending stress. And that can be calculated. Notation is sigma B, bending stress. Now here, while in case of the bending, we know the flexural formula. Flexural formula, that is M by I, F by Y, E by R, T by J, and again T by J is equal to G theta by L. So likewise things are there for the flexural formula. I hope you have learned this. Now here what happened, see, one by one I'll explain. M means bending moment. So I'll write here MB. I means moment of inertia. What is the role of moment of inertia? Moment of inertia resists the bending. That is the important role, moment of inertia. F, here notation is F, it means a stress. Then Y, Y is nothing but neutral axis distance. So suppose shaft is there having diameter D, so its neutral axis distance is D by 2. Always remember. So likewise. Then E, modulus of elasticity. So that depends on material condition. R, this is the radius, we'll have to consider. And T, that is torsional moment. As like we are seeing MB is for bending moment, here torsional moment. So I will write MT for torsional moment. J, polar moment of inertia. Why polar moment of inertia is used? Because polar moment of inertia resists the twist. Whatever be the occur, we have seen one type of the transmission shaft axle which is connected with the two rotating wheel. So at the time of the traveling, there might be chances of the twisting of the shaft because of uneven surface. So to avoid that, we'll have to use for designing of such kind of the shaft polar moment of inertia. After that, G, modulus of rigidity, theta, angle of twist, L, length of shaft. Correct? So likewise we are going to design. So we are here for bending stress. Now what is bending stress? We'll have to consider here. You can see now bending stress, bending moment is here. It means here this equation I can use, and it is related with the stress. So I will have to use these two equations. While considering this, I can write F means stress. So F sigma B I will have to consider. Sigma B is equal to M B Y by I. So this will be the bending stress occur. Now for shaft we need to calculate. Shaft is having circular cross section. So I will have to write bending moment into neutral axis distance. Shaft diameter is D. Therefore D by 2. Moment of inertia, that is pi by 64 D raised to 4. It is for circular cross section of shaft. Now while taking this, if I simplify it in the format, I'll get 32 MB, D get cancelled, by dq. So this will be the equation for the bending stress. So I can write sigma B is nothing but 32 MB by pi dq. So this will be the bending stress we have calculated for shaft. Third is shear stress. So I will have to write shear stress. What is shear stress? Tau. We need to consider the notation as standard notation tau. Shear stress. Now see, shear stress where this is stress. Now this is for the torsional shear stress. Twisting will be occur. So torsional movement is there. So I will have to use this formula. So if I equate these two equations, so I'll write here F by Y is equal to torsional moment or divided by polar moment of inertia. While considering this, I will have to write shear stress means this tau. Tau is equal to MTY by polar moment of inertia. So that I'll get. Now again we need to calculate for the circular cross section. I can calculate MT as it is. Y means D by 2. Then J, polar moment of inertia for circular cross section, pi by 32 D raised to 4. So if I convert this, tau is equal to, this will be 16 MT by pi dq. So this will be the equation number 3. This is equation number 2. Correct? So likewise we have calculated the stresses which are occurred while designing. So important: tensile, bending and shear. So these kind of the stresses we have seen. Now after this we'll have to find out very important thing is that what will be the kind of the theories of failure which is important over here. So see here, while taking this, the two conditions as we have seen the theories of failure, principal stress theory and principal shear stress theory. So here why it is applicable? Because principal stress theory suggested me that the axial and tensile, that is axial means tensile force plus bending. Therefore, I will have to consider according to theories of failure. I'll write according to theories of failure. We'll have to take two conditions. Case 1, I can write case 1. What would be the case 1? Case 1 is sigma x, that is tensile stress, is equal to sigma t plus sigma b. Tensile stress plus bending. So I will have to use this condition, but while using it will consider only tensile and bending. And case number 2 suggested me that it will be sigma x is equal to sigma b. that is axial force is equal to bending. So it includes case number 2, addition of bending as well as a torsion. Correct? While designing. So instead of case number 1 and case number 2, we'll have to use case number 2. While using this, what it indicate? It indicate that sigma x is equal to sigma b. What is sigma x? We don't know. But what is sigma b? We know. This is 32 mb by pi d cube. So I'll write using case number 2, which is equal to sigma x is equal to sigma b, which is equal to 32 mb by pi d cube. 32 mb by pi d cube means wherever be the necessary will have to use sigma x, I will have to direct use 32 mb by pi d cube. Now, as per the theories of failure, first theories of failure, I'll write principal stress theory. Now, what principal stress theory suggested? Principal stress theory suggested that we'll have to use the equation like sigma 1. It can be calculated by Mohr circle also, because theories of failure we can calculate by Mohr circle. So I'll directly, I hope you know the Mohr circle. So I'll directly write the equation, that is sigma x by 2 plus square root of sigma x by 2 bracket square plus shear stress square. So this will be the principal stress theory. Now what we have condition we have decided, that is sigma x is equal to 32 mb by pi d cube. So I will have to put here this value in above equation. Where there is a sigma x, I will have to put. So my value would be, you can see, sigma 1. Now sigma 1 is, it is actually permissible stress, and that can be calculated by SYT by FS, which is equal to sigma 1, correct? Which is equal to sigma x, that is 32 mb by pi d cube. So divided by 2. So I'll directly write 16 mb by pi d cube plus square root of, again divided by 2, that is 16 mb by pi d cube bracket square plus shear stress. How much we have calculated? 16 mt by pi d cube. 16 mt by pi d cube, that is 16 divided by 16, correct? Not divided by 2, so that as it is I will have to write bracket square. Now I'll simplify this. So I'll get sigma 1 is equal to, that is 16 by pi d cube in bracket. So common I have calculated this, mb plus square root of mb square bending moment plus mt square. So this will be your final equation for calculating the stress for solid shaft in case of principal stress theory. Understood? Second theories of failure, which is very important, that can be used, that is principal shear stress theory. So I'll write by using shear stress theory. What it indicates? That is maximum shear stress, tau max. We can make a notation tau max, as here we have taken sigma 1. So tau max is the notation. So I'll write tau max is equal to square root of, instead of this equation we have written sigma 1 is equal to sigma x by 2. Instead of this, the equation will be sigma x by 2 bracket square plus tau square. So here again I will have to put sigma x is equal to sigma b as per the case decided by our side, that is 32 mb by pi d cube. By putting this, tau max is equal to, you can see, square root of, that is 32 mb by pi d cube into 2, that is 16 bracket square plus 16 mt by pi d cube bracket square. So only this bracket I will have to use in case of the maximum shear stress theory. While using this, I'll get, you can see, tau max is equal to, again 16 by pi d cube, I'll take a common, 16 by pi d cube square root of mb square, that is bending moment plus torsional moment square, and this will be the equation for your calculation of the maximum shear stress for designing of the diameter of the shaft. Now here also tau max means it is a permissible shear stress, so it can be calculated by 0.5 SYT by Fs, factor of safety, and MB we can calculate by taking a moment with respect to shaft arrangement. Empty torsional moment will have to consider as per the consideration of the power and RPM of the shaft, so through which here we'll have to calculate the diameter, and that will be the design of shaft. See, design of shaft means we'll have to calculate the diameter of shaft only, that is keep in mind, correct? So two theories of failure we have seen. First one is a principal stress theory, through which we'll get this equation, sigma 1 is equal to 16 by pi d cube in bracket mb plus square root of mb square plus mt square. In case of the shear stress failure, I will have to write tau max is equal to 16 by pi d cube square root of mb square plus mt square, through which we can calculate the diameter of shaft, and that will be the basic design of the shaft on the basis of strength. I hope you understood this session. Do revise it. You can watch a number of times, you will get the idea. So this kind of the derivation will be asked in exam. So derive an expression for a solid shaft or shaft design on the basis of strength. So for that expression you will have to do the procedure like this. Okay, I hope you understood. Thank you.